Hi everyone, this is a video for class 10 of PH 125, and today we're going to be continuing to talk about projectile motion. So just a quick reminder, we've been talking about two-dimensional kinematics, and specifically we've been talking about two-dimensional kinematics in the case that we have constant acceleration. So whenever we have constant acceleration, remember we can use these basic equations of motion that are listed in the teal boxes here. Really, there's 5 equations of motion for constant acceleration for each component x and y when we have two-dimensional motion. But I've listed the 3 main equations that we'll be using here for each set of components, right? So for the x components and for the y components of our position, velocity, and acceleration, all as functions of time. Okay, so really important when using these equations, remember we never want to mix x and y components in the same equation. So whenever you're problem solving using two-dimensional kinematics, you want to be really careful that you're splitting your position, displacement, velocity, and acceleration up into its x and y components, and then only using x components together, only using y components together in these equations. One way that we can relate motion in the x direction to motion in the y direction is by remembering that these two different components of the motion are really happening at the same time. And so they share a common time t, and so we can use that common time to relate motion in the x direction to motion in the y direction, which is something that we'll be doing quite often, and we have a couple of examples in here today. All right, and so one last thing to note here is that oftentimes we aren't actually thinking about final position and initial position. What we're really interested in is displacement. And so you can actually rearrange the top equations in both of these boxes here in terms of displacement. So for example, if you look at the equation, the top equation on the left, if you subtract x naught from both sides of this equation, then you end up with x minus x naught on the left-hand side, which is just our displacement in the x direction, delta x. So that top equation could be rewritten as delta x is equal to v naught x times t plus 1/2 ax t squared. So that's going to be something that's useful for you in a lot of your problem solving. Similarly, we could subtract y naught from both sides of the top equation on the right-hand side here, and then what you would be left with on the left-hand side would be delta y. And so you would end up with delta y, the displacement in the y direction, or how far something has traveled in the y direction from its launch location, for example, if we are interested in a projectile, which is going to be the application we're studying a lot today. Delta y is equal to v naught yt plus 1/2 ayt squared. Okay. And then just one final plug that when you're doing problem solving with 2D kinematics and constant acceleration, you always want to come back to these basic 6 equations in the 2 teal boxes here. So there are going to be some more equations that I will show you that we will derive later on in this lecture, but it's important to remember that those are derived for very specific circumstances, so very specific initial conditions, for example, whereas these guys in the teal boxes are general and you can always use them. So I highly recommend coming back to these equations. All right, with that in mind, let's take a look at our projectile motion types of problems. So remember, projectile motion is an example of motion in 2 dimensions with constant acceleration, and it's something that you'll see a lot in problem solving in this class. All right, so whenever you have a projectile, you're going to get a problem statement, and it's really important to be able to read that problem statement and pull out relevant information that you can plug into those 6 equations of motion for constant acceleration. So just as an example here, say you have a problem statement that says something about a projectile that's launched with a speed v naught at an angle theta naught above the horizon. All right, so first thing I would pick out of this, we have a projectile. And so that means that we immediately know that ax is equal to 0. There's no acceleration in the x direction. Nothing is acting on the object after it gets launched to cause it to accelerate in the x direction. So there's no acceleration in the x direction, ax is equal to 0, and we know that the thing that's acting on the projectile in the y direction is gravity, and that causes an acceleration of ay is equal to minus g. Okay, so you can always go ahead and write down these 2 known conditions whenever you get a problem with a projectile. Okay, the next thing I see in this particular problem statement is that we're given the launch speed, so that's v naught, and the launch angle, which is theta naught. And so whenever you're given the launch speed and launch angle, really that's telling you about the initial velocity vector here, so the vector v naught. And we know that to use our equations of motion with constant acceleration, we're going to have to break that vector up into its x and y components, v naught x and v naught y. So to do that, you'll want to make a little sketch here where you draw in your velocity vector and make it so that it's at an angle above the horizontal or above the horizon of theta naught, so that's that launch angle. And then you can see that from trigonometry that we get v naught x is equal to v naught cosine of theta naught, and v naught y is equal to v naught sine of theta naught. Okay, so those are going to be your initial velocity, the initial components of the velocity in the x and y direction, respectively. Okay, and so then those would give you some knowns that you could plug into your equations of motion, those basic 6 equations, to go about solving your problem. So now we're going to spend some time studying some other things that you might be asked about in a projectile motion type of problem. So something that comes up commonly are questions about what's happening when the projectile reaches its maximum height, or you might hear it referred to as its peak. So when we think about a projectile, when it reaches that maximum height or its peak in its trajectory, it turns out that the vertical component of the velocity right at that moment in time when the projectile is at its peak is always equal to 0. So let's see where that comes from. And to do that, I've made a plot of the vertical position of a projectile as a function of time. I've made this plot using some assumptions here. So first of all, I assumed it's launched from the ground. So it's launched from 0 height. I also have it landing at 0 height here. I've also made the assumption that the launch speed is 15 meters per second and the launch angle is 55 degrees. And then I just used my basic equation of motion for the y position as a function of time to make the plot on the right-hand side. Okay, so then looking at this plot, we can pick out the vertical height of the projectile when it reaches its peak. And so that's what I'm going to call y max here. So it's just the maximum height of the projectile, or you might see it referred to as y peak. So it's the vertical height at the peak. Okay, and so then we want to think about how do I relate this position versus time graph to the speed of the projectile? Well, remember that position versus time graphs have the special property that the slope of the position versus time graph at a particular moment in time corresponds to the speed of the object. And so here specifically, we're thinking about the instantaneous speed right at the peak, and this is a plot of the y position versus time. And so then the slope of the tangent to the curve right at that point is going to tell us about the vertical component of the velocity right at that point in time at the peak in this projectile's trajectory. Okay, and so I've drawn in the tangent to the curve at that point, and you can see that it's a horizontal line, right? And that's always going to be the case right at the peak of the projectile's path. Okay, and then we know that the slope is going to correspond to the vertical component of the velocity right at that moment in time. For a horizontal line, we know that slope is 0. And so in other words, we see that we always get this case that the vertical component of the velocity right at the peak is equal to 0. Now I will make the note here that that's not the same as the x component of the velocity. We know that the x component of the velocity of this projectile is going to be constant, so it's going to be equal to the initial value of the x component of the velocity, right? Because there's no acceleration in the x direction. So we know that right at the peak, the projectile is still moving in the horizontal direction. It's just not moving up and down anymore right at that particular moment in time at the peak. So in other words, Vy at the peak is going to be 0. Okay, and this is analogous. Remember when we were thinking about free fall in one dimension, when you throw an object up in the air and it falls back down? There's that moment right at the peak in that object's trajectory as well, where it stops for just a moment, where it turns around and then it comes back down, right? So this is analogous to that. Okay, let's do some practice in working with projectiles. So first of all, we have a cannon that's fired with an initial speed of 650 meters per second at a launch angle of 40 degrees above the horizontal. We want to know what is the cannonball's initial speed in the y direction. Okay, so to answer this question, I would go ahead and sketch it out. So first of all, we want to sketch out the velocity vector, the initial velocity vector, v naught, which we know is going to have a speed or a magnitude of 650 meters per second and a launch angle of 40 degrees here. All right, then we could sketch in the x and y components of the velocity. Here we're specifically interested in the initial velocity in the y direction, and so that means we're really just interested in the y component here. So you could think about this little right triangle that's formed by the x and y components of the initial velocity, and from that little right triangle we see that v naught y is going to be equal to v naught times sine of theta naught. Okay, from there it's pretty straightforward. We just want to plug in that v naught, the launch speed, is 650 meters per second. The launch angle is 40 degrees. You want to make sure your calculator is in degrees, and you should end up getting 417.8 meters per second, which, looking at our answer choices, we could round to 420 meters per second and pick answer C here. Okay, next question. It's the same setup, and we want to know what is the cannonball's vertical speed when it reaches its peak. Okay, so for this one, we just have to remember that the vertical speed of any trajectory at its peak is 0. And so then we should pick answer D here. So like I mentioned, this is just the vertical speed. We know it would still have some horizontal speed right at that peak, but the vertical speed at the peak is always equal to 0. And that's something that won't be stated to you in a problem like what we have here. So in general, you would just get this form of the problem, right? So we just are told that this cannonball is fired out of a cannon, and then we want to know how long does it take for the cannon to reach its maximum height. And so in solving a problem like this, when you see the maximum height, you immediately have to remind yourself that you already know something about the cannonball at that maximum height. You know that the y component of its speed at that height is going to be 0. Okay, so go ahead, try it out, see if you can go ahead and solve this problem and find out how long it takes the cannonball to reach its peak. Okay, so to solve this problem, we want to start by listing our known quantities here. So first of all, we know this is a projectile. The cannonball is our projectile. And so we already know that AY is equal to minus G, or in other words, minus 9.8 meters per second squared. And we know that AX is equal to 0. All right, next thing, we're told the launch speed, which is 650 meters per second, and also the launch angle, which is 40 degrees. Then we already used this information to find the y component of the initial velocity. We could also use this information to find the x component of the initial velocity. So to do that, we would just use v naught x is equal to v naught cosine theta naught, and we would get 498 meters per second. Just a reminder, we already found v naught y in a previous part of this problem, and we found that it was equal to 418 meters per second. Okay, and then our last bit of known information here really comes from the fact that we're interested in the situation where the cannonball is reaching some final position when it's at its peak, right? So if we were to break this problem up into like an initial situation and a final situation, the initial situation when time t equals 0 is going to be the time when the cannonball is fired. So it's all the properties of the cannonball right when it's fired. And then when we think about the final situation in this problem, we're really just going to be interested in all the properties of the cannonball when it reaches its peak. And so what that means is that we're going to be interested in a final speed of that cannonball when it's at its peak, and we already know something about that. We know that Vy when it's at its peak is equal to 0. Okay, so Vy in this case is equal to 0, and that's that hidden bit of information due to the fact that we're interested in when the cannonball reaches its peak. Okay. Then we can write down our unknown in this case, which is how long it takes the cannonball to reach that maximum height, which I'm calling t peak. So how do we find the t at the peak, how long it takes the cannonball to get to the peak? Well, we look at our list of 6 equations for constant acceleration, and we look for one where the only thing that we don't know in that equation is time t, because that's really what we're looking for here. And so when I look at those equations, I see that we have one that looks like Vy is equal to V naught y plus AYT, and we know Vy, that's going to be the velocity at the peak, so in other words, the velocity at time t, which is t peak, and we know that Vy is equal to 0. We already found V naught y here, and we know AY is equal to minus g. So we can just go ahead and plug in that information. I've done that here, and then all we have to do is rearrange and solve for t at the peak, which when I did that, I ended up getting 43 seconds, and so I would go ahead and pick answer B here. Okay, so in addition to thinking about what's happening to our projectile when it reaches its peak, something else that's really interesting to think about is where is the projectile going to land? So this is something that's going to come up quite often, and where the projectile lands is referred to as the range. So in other words, the range is going to be the horizontal displacement of the projectile before it reaches the ground. All right, so just a little bit of jargon here. Usually when we say when the projectile lands, we're referring to the place where y is assigned to be 0. So oftentimes you create your coordinate system, you assign your coordinate system so that y is equal to 0 at ground level. And so then when the projectile lands, it's going to reach a level where y is equal to 0. So that's something to keep in mind. And for us, we want to think about how could we change the range of a projectile. So that means that we want to come up with an equation that relates our motion, our initial conditions of the motion of this projectile to the range of the projectile that results. And so we're going to do that for a very specific example. So our example that we're going to look at is a projectile that's launched with a speed v0 at an angle theta naught. And specifically, we're going to be thinking about a projectile that lands when it reaches its initial height. So in other words, it's launched from the ground and it lands at the ground, just like the little figure that I have drawn in up here. In other words, we could say y is equal to y naught. Okay, and so then for this example, our goal is going to be to find delta x, or in other words, the range. And so to do that, let's start by listing out our knowns. Okay, so first of all, we know it's a projectile, so we can write down ay is equal to minus g and ax is equal to 0. We also know that it's going to be launched at some launch speed. We're leaving it generic here, so we're just going to leave it as v0, and then it has a launch angle theta naught. So then we could think about drawing out our little initial velocity vector in terms of its speed and its launch angle to find the x and y components of the initial speed. We would get v0x is equal to v0 cosine of theta naught, and v0y is equal to v0 sine of theta naught. All right, and then our last bit of information here that's specific to this example is that we know that we are assuming that the projectile is going to land where it's launched from. So in other words, y is equal to y naught. And then we could rearrange this for delta y. Remember, delta y is equal to y minus y naught, right? So it's the final position in the y direction minus the initial position in the y direction. And so then since those two things are the same, we can see here that the displacement in the y direction is going to be equal to 0. All right, next up we want to list our unknown, which is the range, or in other words, delta x, the displacement of the projectile in the x direction before it lands. All right, and so then to go about solving this problem, we want to do what we've always been doing here, which is to look at our 6 basic equations of motion for constant acceleration. And we want to look for one where we can solve for delta x because it's the only thing that we don't know in our equation. Everything else is one of our knowns. If you look at these equations, first of all, we can rule out the bottom 3 here, right? Because those are all in terms of y components. So we can rule those out immediately, narrow things down to 3. Then looking at these equations, I see that only the top and bottom equations contain delta x, which is the thing we're looking for, right? So that's narrowed it down to 2 already. Now let's look at the top one here. We know that we have v0x, right? So that's okay. We know ax, but we don't have t, right? So we don't know the time that it takes for the projectile to land. And so we can't use that one to find delta x, at least not right away. This one we said we couldn't use, it doesn't contain delta x. And then if we look at the bottom equation here, if we were to think about plugging in our knowns, ax is equal to 0, right? And so when you plug that in, that simplifies the equation down to vx squared equals v0x squared. So it actually won't tell us anything about delta x. So we're not going to be able to use that equation either. So that means that we have to be able to find t first to be able to use this top equation to find the range of our projectile. All right, so we're going to have to find t, which is the total time that it takes the projectile to land. This is referred to as the time of flight, remember? And how are we going to find the time of flight? Well, it turns out that we can actually find this by analyzing the motion in the y direction. So if you look at these equations, now we're going to try to find an equation that we could use to find t using all of our known values here. So if you look at these equations, I see immediately this top equation looks like a good candidate. We know delta y, we said that the y displacement is 0. We know v0 y, we know ay, and so then our only unknown here is going to be t, the time of flight. Okay, and so that's going to be our approach. We're going to find the time of flight first, so we're going to find t first, and then we can plug that in here and we'll be able to use the top equation in the top blue box to be able to find our range. Okay, with that in mind, let's go ahead and find our time of flight. Again, we're going to start with delta y is equal to v naught yt plus 1/2 ay t squared. And then we can just start plugging in our knowns here. So we know delta y, the displacement in the y direction, is 0. We know v naught y is v naught sine of theta naught. And then we also know ay is equal to minus g. So I've just plugged that in, and now my goal is going to be to solve this for t. So first of all, I'm just going to rearrange. You'll notice that both of the terms on the right-hand side have a factor of t in them. So you can pull one factor of t outside and put the whole thing in parentheses, right? So I've just factored out one factor of t. Okay, and then what you can see here is that there's actually two ways that you could get 0 out of this equation. So the first way would be if you just plugged in t equals 0. And that comes from the fact that we already assumed that y, which is the position at time t, is equal to the initial position. So of course that's going to be true when t is equal to 0, right? So that makes sense that we would get that solution out. The second solution is going to be more useful to us here, and that's by making this term in the square brackets equal to 0. And so when we do that, we get v naught sine of theta naught minus 1/2 g times t is equal to 0. So that guy we're going to be able to use to solve for the time where our projectile is going to land. Okay, and so then if I were to do that, it's just a little bit of algebra over here. I'm just rearranging and solving for t, and what I got is that t is equal to 2 times v naught sine of theta naught divided by g. Sometimes you'll see the time of flight referred to as capital T, so that's just the total time it takes for the projectile to land. All right, and I'll just remind you that this is for the specific case where the projectile is launched and lands at the same height. All right, so now we have our time of flight, so we know t, and we're going to be able to use that to find our range. So let's go ahead and think about finding the range, or in other words, the displacement of the projectile in the x direction. So how do I do that? I go from my general equation here, x is equal to x naught plus v naught xt plus 1/2 a xt squared. I just rearranged it and got it into the form that we have delta x is equal to v naught xt plus 1/2 axt squared by remembering that delta x is really x minus x naught, the final position minus the initial. Then I just went ahead and I plugged in my known values from my list over here on the left-hand side. So we know v naught x is equal to v naught cosine of theta naught. We also know that the acceleration in the x direction is 0, which is wonderful. That's going to simplify things quite a bit here. Next thing, I just plugged in my time of flight, which we found from analyzing the motion in the y direction. So I plugged in that time of flight for my time t here, because remember, that's going to be the final time in this particular problem. So I plugged in my time of flight, and then the last step is actually just one simplification here, which comes from using a trig identity. Don't worry if you don't remember this trig identity. You are not expected to remember it. We're just using it here because it's going to make our future analysis of how we can change the range of a projectile a little bit easier. So the trig identity here is that 2 times the cosine of some angle multiplied by the sine of that same angle is equal to sine of 2 times that angle. So I've just plugged that in here. I've replaced 2 times cosine times sine with sine of 2 theta. All right, and so then what we get is this simplified version of the range delta x, which is v naught squared over g multiplied by sine of 2 theta naught, that launch angle. All right, and sometimes this is referred to as capital R for the range. Okay, so again, this is going to be the range of a projectile that's launched and lands at the same height. Okay, so this is wonderful because this gives us a way that we can analyze ways that we could change the range of a projectile for the specific case where it's launched and lands at the same height. So that would be the only time that you would want to use this equation. So just a little warning there again. Okay, so we have our equation. I've rewritten it here, and we want to use this to analyze our range. So specifically, a lot of the times when you're thinking about projectiles, you'll be thinking about, how do I maximize my range? How do I get this projectile to go as far as possible? So if you look at this equation, there's really 3 things that we could imagine changing to change the range of our projectile. So you could change the launch speed, so that's v naught. You could change the launch angle, so that's going to be theta naught. Or if you go to another planet, you could change the acceleration due to gravity. So that's not really very realistic, right? So our 2 main options for changing the range are going to be changing the launch speed and changing the launch angle. All right, so let's first of all think about how we could maximize the range by changing the launch speed. So we see here from our equation up above that the range is proportional to v naught squared. And so what that means for us is that if you were to increase the launch speed by a factor, say if you increased it by a, so the launch speed was a times some original launch speed, then what would end up happening is you would increase r by a squared. So what that means for us here in terms of how do we maximize the launch speed, really, how do you maximize the range? Really, you just want to maximize the launch speed, right? So if you increase the launch speed, you're going to increase the range. So you just want that guy to be launched as fast as possible if you want your range to be as long as possible. Okay, so now the second way that we could think about changing the range of a projectile is by changing the launch angle. So how do we maximize the range by changing the launch angle? Well, here we're going to have to think about this sine function. So what does that sine function really do? So a sine function, I have sine of some angle. I'm just using a generic angle here. So phi is just a generic angle. So I've plotted sine of phi as a function of phi in degrees here. And so you can see that it oscillates between -1 and 1. And that's always going to be true for the sine of an angle. And so what that means is that the maximum value of the sine function is always going to be 1. Okay, and by looking at this plot, we can see that the maximum value of 1 occurs when our angle is 90 degrees. Okay, so what does that mean for us in terms of our range? If we want to maximize the range, then we want to maximize sine of 2 theta naught. And we know that the maximum value of any sine function is always going to be 1. So that means that the maximum value is going to come when sine of 2 theta naught is equal 1. So then we learned that the sine of phi here was maximized for phi equal to 90 degrees. So that means the entire argument of that sine function is going to be 90 degrees to get that maximum value for sine equal to 1. And so what that means here is that we want 2 times theta naught to be equal to 90 degrees, or in other words, we want our launch angle theta naught to be 45 degrees to give us a maximum range for our projectile. Okay, and so here we can plot range as a function of theta naught, and you can see that yes, in fact, you do get the maximum range here when your launch angle is 45 degrees. And then one last note here, if you do launch your projectile at a 45-degree angle, you know you're going to get sine of theta is equal to 1, and so you can see that the maximum range you could get in that case would be equal to v naught squared divided by g. Okay, so then our last topic in thinking about projectiles is projectile symmetry. And so just like when we were studying free fall, remember there was nice symmetry of the motion of an object in free fall. It turns out that there's nice symmetry for an object in projectile motion as well. So we're going to go through some key points here, and then I'll go over the symmetry in more detail. But just as a little key here, I'll remind you that capital T refers to the total time of flight, so how long it takes a projectile to land, and capital R refers to the range, or in other words, delta x, right? So the displacement in the x direction of that projectile. And all of these points are derived for a projectile that is launched from the same height from which it lands. So in other words, y, the final height in the y direction, is equal to y naught, the initial height in the y direction. So these things are only true for that particular case. All right, so our first point for our symmetry here is that it turns out that the time it takes the projectile to reach its peak height is exactly half of the total time of flight of that projectile. Then it turns out that the x displacement of the projectile when the projectile reaches its peak height is exactly equal to half of the total range of the projectile. The next two things are all about the velocity of the projectile. So it turns out that the speed of the projectile when it lands is exactly equal to the launch speed. And finally, we're interested then in the direction of the velocity of the projectile, and it turns out that the direction of the velocity when the projectile lands, so I'm calling that theta land, is equal to minus the direction of the launch angle. So in other words, it's equal to minus the launch direction. Okay, so let's go ahead and study each of these pieces of information about symmetry in a little bit more detail. And I'll just remind you that all of this analysis depends on the fact that y is equal to y naught. So in other words, the landing height is equal to the launch height. Okay, so we'll start with position versus time, specifically vertical position as a function of time. I've plotted it using one of our basic equations of motion, and I've just plotted a data point every 0.2 seconds here. So looking at this plot, we can see that the time it takes the projectile to reach its peak is exactly half of the total time of flight. So let's look at that in a little bit more detail here. First of all, let's identify the total time of flight. So in this case, it's going to be about 10 seconds, it looks like, right? So remember, that's how long it takes the projectile to land. Then we can identify the maximum height of our projectile and drop down a vertical line to find out how long it takes that projectile to reach its maximum height. So here, when I drop down that vertical line, I see that the time it takes the projectile to reach its peak is exactly equal to 5 seconds, which is half of the total time of flight. So in other words, t peak is equal to capital T, the time of flight, divided by 2. All right, next let's think about y position versus x position, where here I've plotted these data points all as functions of time, and I've plotted a data point every 0.2 seconds. So to create this plot, I've used the relationship between y at a particular time and x at a particular time that we derived at the end of the last video lecture. Okay, and so now looking at this plot, we can see that the x position, or the displacement in the x direction, when this projectile reaches its peak is exactly half of the total range of the projectile. So let's take a little bit closer look. First of all, we can identify the total range of this projectile. It's the length of that blue arrow there, which looks like it's about 850 meters to me. Then once again, we can identify the maximum height, or the peak height, of this projectile and drop down a vertical line to think about the displacement of that projectile in the x direction when the projectile reaches its peak. So then looking at this, I would say that that delta x at the peak is equal to 425 meters, which is in fact half of the total range. So this is the general result here, is that delta x at the peak is equal to the range divided by 2. Okay, so the next thing we want to think about here is the velocity, the magnitude and the direction of the velocity. And again, this analysis is just when the landing height is equal to the launch height. So we'll start with the magnitude of the velocity, or in other words, the instantaneous speed as a function of time. So I've made a plot of the instantaneous speed as a function of time using the square root of vx squared plus vy squared, where remember vx is a constant, it's equal to the launch speed in the x direction, and vy is given by one of our basic equations of motion. Specifically here, we're using v naught y minus g times t. And again, I've plotted one data point for every 0.2 seconds. Okay, so then looking at this plot, we can see that the speed when the projectile lands is equal to the launch speed. So let's go ahead and identify the time when the projectile is launched is time t equals 0. The time when it lands is our time, capital T here. So that's our time of flight, which we said was 10 seconds for this example. So then if you want to identify the speed of the projectile at those two particular moments in time, you would just want to trace upwards, trace a vertical line upwards from t equals 0 and time t, which is our time of flight. And then you can see that these 2 points, these 2 data points, both fall on the same horizontal line, which corresponds to the initial speed, v naught, and we see that that is in fact equal to the landing speed then. Okay, then we also have one last thing to notice from this plot, which is that the minimum speed of our projectile occurs when the projectile is at its peak. And this makes sense because we know that at the peak, the y component of the speed has to be 0. And so then the overall speed of the projectile right at that moment in time is just going to be given by vx. So that makes sense. Okay. Next up, let's think about the direction of the projectile velocity as a function of time. So I've created this plot. Again, I've used vx and vy like from up above, and now I'm just plotting the angle theta that results from the inverse tangent of vy over vx. Okay, so looking at this plot, we can see that the angle at which the projectile lands is equal to minus the launch angle. So let's go ahead and look here. We can identify the time t equals 0. That's going to be the launch angle, right? So that corresponds to our launch angle here, which we see is going to be 30 degrees. And then if you think about the time when the projectile lands, remember that's our time of flight, capital T. We said that was 10 seconds in this example, and here you can see that that does in fact correspond to a landing direction of minus 30 degrees, which is in fact minus the launch angle. All right, one more thing to notice here is that the direction of the velocity at the peak is equal to 0, or in other words, the velocity when the projectile is at its peak is all horizontal, which is something that we've already mentioned a few times today, right? And so this makes sense to us because we know that at the peak, Vy is equal to 0, and so we would get an angle for our velocity of 0. In other words, the velocity is all horizontal at the peak, and you can see that that is in fact the case here, which occurs when t is equal to half of the total time of flight, or in other words, 5 seconds in this particular example. Okay, so our last thing that we're going to talk about in terms of the symmetry of projectile motion is the symmetry in the range as a function of launch angle. And for this, we're going to look at a plot of range as a function of launch angle theta naught. And here we're using the equation for range as a function of launch angle that we derived earlier today, which I'll remind you was only true for the case that the projectile is landing at the same height from which it is launched. Okay, so I would get the resulting plot up in the right-hand corner here. And from this plot, we can see that the range is in fact maximized when the launch angle is 45 degrees. So if we think about the maximum range here, if you were to draw out that maximum range and drop down a vertical line, you can see that yes, it does in fact occur when the launch angle is 45 degrees. Then we can also see that there's some nice symmetry in terms of when you move away from 45 degrees, what happens to the range. So for example, if you were to move a certain amount of delta theta in the positive direction or a delta theta in the negative direction away from this 45 degree launch angle, you would end up getting the same range. So for example, if you were to think about launching the projectile from 30 degrees, in which case we're subtracting 15 degrees from 45, or at 60 degrees, in which case we would be adding 15 degrees to 45, you can see here that you would end up getting the same range in either case. Okay, so there's some nice symmetry there. All right, and then we can also see that same symmetry by plotting our position as a y position as a function of x position for those three different launch angles that I mentioned up above. So for 45 degrees, that's in orange here. For 60 degrees, that's in yellow. And then for 30 degrees, I have it plotted in blue. And you can see that we really do get the largest range, so the largest displacement in the x direction when the launch angle is 45 degrees. And you can see here that you get the same range when the launch angle is 30 degrees as when it's 60 degrees. All right, so let's wrap up our discussion of projectiles with one last practice problem here. And this practice problem should be pretty straightforward. So if you're doing a lot of math, you're doing too much. Okay, so here we have a projectile that lands at the same height as its launch height. And if it lands after 4 seconds in the air, we want to know how long does it take to reach the peak height. Okay, so this question is really simple if you remember the symmetry of projectile motion, which tells us that the time it takes the projectile to reach its peak is exactly half of the total time of flight. So here we know the total time of flight was 4 seconds, since it lands after 4 seconds in the air. And so that means the time it takes to reach the peak is going to be exactly half of that, or in other words, 2 seconds. And so we should get answer C here. Okay, so that pretty much wraps up chapter 4. It also pretty much wraps up our study of kinematics. We're going to be moving on now to dynamics. So remember, kinematics was like the basic study of motion, and dynamics is more the study of how motion is created. And so when we talk about dynamics, the first place we start is with Newton's laws of motion. Okay, so before we can dive into Newton's laws of motion, we need to define two terms, inertia and mass. So we'll start with inertia. Inertia is really just resistance to motion. So it's an object's property that is resistance to motion. And then mass is defined as the measure of inertia, or in other words, it's a measure of how difficult it is to make an object move. Okay, so the way I like to think about this is if you push on a book, it's relatively easy to move, and if you push on a car, it's much harder to move. So to me, that means that the car must have much more inertia than the book. In other words, the car has more mass than the book. All right, and so that makes sense, right? That correlates to our understanding of mass that you probably have from other classes. Okay, another way that we talk about mass, which is probably the more familiar way that you've heard mass defined, is it's a measure of how much matter an object has. And so this is also a good definition. For example, if you think about a book, it's small and it's fairly dense. A car is much larger, but it's still fairly dense. And so then I would say that the car probably has a lot more matter in it than the book. And so in other words, the car has more mass. Okay, so these two definitions, they're both good. All right, so then just a quick reminder, the SI units of mass are the kilogram, which is 10 to the third grams. Turns out grams is pretty small, and so SI units, we always want to be talking about kilograms. Okay, so now we're ready to get back to our big question, which is why do objects move? So it turns out that motion is due to forces, which are defined as a push or a pull. So for a force, we use the symbol F. You'll notice here it's bold and it has an arrow over it, which tells me immediately that it's a vector. The SI units of forces are newtons. A newton is a kilogram meter per second squared, and we will show why that's true in a little bit. So some examples here. The Earth exerts a force on you, that's gravity. We call that F sub g, so F with a little g for the force of gravity. So this is actually why when we talked about all that stuff we've been talking about, free fall and projectiles, when we talk about, the only thing acting on the object is gravity, the thing that's really acting is the force of gravity. So we're now introducing that thing more formally, it's the force of gravity. You also exert forces all the time. So for example, pushing a shopping cart, pulling a kid on a sled, or you exert a force even on your pencil as you write. Okay, and yes, just another reminder, forces are vectors, as I mentioned, and so they have both magnitude and direction. All right, and so let's just do a quick reminder working with our X and Y components with forces. That is one thing that is not going away. So we still have to remember how to split things up into X and Y components so that we can work with forces. So here's an example. I have a shopping cart. I'm exerting a force of 5 newtons 30 degrees below the horizontal on the cart, and I want to know what is the horizontal force that I exert on the cart. So how would I do this? First thing I would do is I would sketch it. So that would be my first approach to this. So I'm exerting a force. My force is 5 newtons and it's applied at 30 degrees below the horizontal. So in other words, that's going to be an angle theta of minus 30 degrees that I have drawn in here in blue. So my vector for F is really this blue arrow that I have pointing 30 degrees below the horizontal. All right. And so now all I want to do is find the horizontal force that I exert on the cart. In other words, that means I want to find Fx, right? The x component of that force. So how am I going to do that? With our lovely trig, right? So we remember that Fx in this case, it's adjacent to my angle theta, which means that Fx is going to be F cosine of theta. F is 5 newtons and theta is minus 30 degrees, and so I find that my force in the x direction is going to be 4 newtons here. Okay, so now that we know a little something about inertia, mass, and forces, we're ready to get to Newton's laws of motion. So Isaac Newton defined these 3 laws of motion, which relate how an object moves to the forces that act on the object. We're just going to briefly introduce them today. We're going to go over them in much more detail in future classes. Okay, so the first law is the law of inertia. I do have a note here that he borrowed it, we'll say, from Galileo. So the law of inertia, colloquially, you might have heard it, that an object at rest tends to stay at rest. So that's kind of like the shorthand version of the first law. The second law really is telling us that the force acting on an object is equal to its mass times the resulting acceleration, or in other words, the resulting acceleration is equal to the force divided by the mass of the object. And the third law is another one that you've probably heard. This is the law that tells you that for every action, there's an equal and opposite reaction. So it's used all the time, not necessarily applying to physics, but in physics, what that really means is that for every applied force, we call it an action force, there's an equal and opposite reaction force. Okay. That's it for Newton's laws for today. Like I mentioned, we're going to go over these in much more detail in future classes. And so I will see you in class.